A voltage gain close to unity is what you can expect from a properly designed Darlington amplifier. But the added advantage is that characterize-wise, input, very high impedance. So you will be able to connect even a signal source of fairly larger input impedance without much loading problems, because the input impedance of Darlington pair amplifier is going to be practically, in most cases, a few hundreds of kilo ohms. And the output impedance is going to be very small, of the order of a few ohms, which are, essential requirements to make a high impedance signal source to drive a low impedance source. So that's the buffering. So here you can see that we are using, as suggested, it's a Darlington pair amplifier because we are using two common collector amplifier stages. Common collector amplifiers are otherwise called emitter followers, because the output across the emitter always follows the input in amplitude and in phase. That's why we call it an emitter follower as well. Two emitter follower stages, Q1 and Q2, are the two transistors. I've chosen SL100 instead of BC107. It's a low power transistor. The maximum power dissipation of BC107 is just 300 milliwatts. For SL100, I think it is around 1 watt. I'm not that sure. You can go for 2N3055, which is very commonly available. 2N3055 transistors, which are high power transistors. We can design Darlington pair if you require larger buffering, larger current amplification. So here, the design idea, we are used base resistor biasing technique. Of course, you can use potential divider biasing technique, which we have done in the previous circuit, which consists of combinations of R1 and R2. Here, we have just a resistor RB as part of the biasing circuit, and of course RE. RE here acts both as part of the load as well as a component required for providing biasing. As per the circuit, you can follow the Kirchhoff's voltage law and see that the total potential drop across RB is equal to the applied potential VCC minus a small drop here, minus this here, and minus this here. You have to choose RB with such a magnitude that the potential drop across RB should be so adjusted, which will follow a relation which I am just going to write on the board. VRB is the potential drop across RB, has to be VCC minus 2 times this minus this, which follow from symbol KVL, Kirchhoff's voltage law consideration for that closed loop. The total potential applied is your VCC. We are discussing the DC biasing of the circuit. So the total potential VCC applied between this point and the ground, a portion of that comes here, a portion of that comes here, then here, then here. So that will complete the loop. So according to this relation, you can fix RB. Now, what should be the value of RB? Now, to find the value of RB, we know VCC is 9 volt. We are using SL100, which is again silicon transistors. So in order to just forward bias the base emitter region, we require some value around 0.7 volt. So 9 minus 2 into 0.7, 1.4. Then we provide a small drop across RE. I think I can just show everything in the next slide. So this last one. drop across RB equal to VCC minus VRE minus 2 VBE. So from that you can calculate RB. Now, as in the previous case, while you designed the ordinary common emitter RC coupled amplifier, we allowed a voltage drop 50% of VCC across collector and emitter. That's a primary requirement to provide maximum voltage swing on both sides of your active region, right? So VC should be almost 50% of whatever supply voltage is provided. In our case, it's 9. So 50 volt is dropped across the collector and emitter. The remaining, you can see here. So once we provide with that much across the collector and emitter, the remaining 50%, can be dropped here. Again, the consideration is to fix the Q point affordably in the sense so that the output and input will get faithful amplification for the signal in the output. So once we fix that, so let's complete this calculation. So it's 9 minus 1.4 minus, we have VRE equal to 50% of VCC, which is equal to 4.5 volt. IC is the nominal DC quiescent value of DC current that should flow in the output of your Darlington pair amplifier, which actually is decided by your buffering requirement. In this case, I have taken it to be around 10 milliampere. Since it is SL100, you can take it, say, 20 milliampere or 30 milliampere or around that value, 40 milliampere is okay because SL100 is a medium power transistor. If you require more current, of course, you will have to use some high power transistor like 2N3055. This is very easily available. We'll be using this transistor maybe in some other circuits. 2N3055 has an IC nominal value, not nominal value, IC maximum value of 4 amperes. So for higher buffering requirements, you can use 2N3055 or similar type of high power transistors. Now in this we have used SL100 and we have designed IC to be at 10 milliampere. You can of course do it in your lab for 20 or 25 milliamperes. So once IC is 10 milliampere, VRE is 4.5 volt. RE can be calculated as, RE you know is IE into VRE equal to IE into RE equal to 4.5. So obviously RE, Ohm's law, 4.5 over IE. IE is approximately equal to IC, assumed to be somewhere near 10 milliampere. So that will give you 450 ohms. Nominal current normally. I don't remember the nominal current value for 2N3055. Of course, you can look up in the data sheet which is readily available in the net. So we get RE to be somewhere at 450 ohms. Now, in order to find the value of RB, we should know beta 1 and beta 2. I've assumed beta value for SL100 to be somewhere near 180. So if beta is 180, you see that the total beta of the circuit is equal to beta 1 into beta 2. That readily come into picture because the emitter of the first stage is driving the base of the second stage. So if the base current of the first stage is IB, the emitter current is close to beta 1 IB, and the emitter current of the second stage is going to be beta 1 into beta 2 IB. Because we are using both transistors in common emitter configuration. So if IB is the base current for the first stage, the collector current which is close to the emitter current for the second stage is beta 1 into beta 2 into IB. Now instead of beta 1 into beta 2, I'm going to replace it with beta. so that I can consider the pair of the two transistors to be equivalent to a single transistor. A single transistor whose beta equal to beta 1 plus beta 2, whose IB is the base current which we provide by biasing in the first stage, whose IC is the collector current in the second stage, which we have taken, in our case, we have taken that to be equal to 10 milliampere. So I can write this equation, IC equal to beta 1, beta 2 IB. In our case, it is 180 into 180 IB. So since IC is equal to 10 milliampere by assumption, IB equal to 10 milliampere over 180 into 180. So that will give you the base current requirement as per this design. That should be the amount of base current that should flow into the base of the first transistor as per our design. So once you know IB, make this calculation. So you know we have VRB equal to 9 volt, which is VCC, minus 2 times VBE, which is equal to 1.4 volt, minus the voltage drop across RE, which we have taken to be equal to 4.5 volt. So this is going to be, is it 3? 3.1 volt. So VRB is going to be 3.1 volt. VRB is the drop across RB, which is IB into RB. See that we have made use of base resistor arrangement. You can see the current from VCC flows through RB, DC current through RB, and goes as IB. So IB RB equal to 3.1. So RB equal to 3.1 over IB. IB can be calculated here. We have done the calculation here. This is your IB. I think I have done the calculation. I have got RB to be somewhere near 10 mega ohm. You can, of course, you can always choose the resistor which is close to your calculated value. So I think it should come around 10 mega ohm. So RB is taken to be 10 mega ohm. Ci and Co, which are the coupling capacitors, which we already have discussed why we have to use the coupling capacitors, which of course will decide the low frequency response also. That is conventionally taken to be 1 microfarad. We can derive from the AC equivalent circuit of a Darlington pair, we can derive this relation. The voltage gain VO, which is the output across RE, VO by VI is going to be RE over RE2 plus RE, where RE2 is the dynamic resistance of the emitter diode of the second transistor. At the operating point, we are fixed. The second transistor, the output is taken across the second transistor from the emitter resistance connected. And the voltage gain theoretically is given by this relation. Again, the derivation steps, you can find it in a standard book which will deal, which deals Darlington pair amplifier circuits. Now, you can see from that relation that RE2, of course, is the dynamic resistance of the PN junction, which is going to be too small, of the order of a few ohms. In our case, no. In our case, for the second transistor, IC was 10 milliampere. So RE2 is going to be VT over IC, which we have already discussed. VT is the thermal voltage. Now, if you are assuming that we are operating it around 27 degrees Celsius, this is going to be RE2 is going to be millivolt. In the last session, I have shown you how the thermal voltage comes to 26 millivolt for 300 degree Kelvin operating temperature. over 10 milliampere. So you can see it is just 2.6 ohms. It's too small. All for common collector amplifiers or for all buffer amplifiers, by definition, a buffer amplifier operated higher collector currents. So since the collector currents are higher, the dynamic emitter resistance will be small. So in that, we have RE divided by RE2 plus RE. Numerator is slightly smaller than the denominator for the voltage gain expression. So obviously the gain is going to be just below 1. If you design it properly, you will get a gain as close to 1. Maybe sometimes we'll get it to 0.96 or 0.97, somewhere near that. Now the input impedance actually is determined by both stages together. The total input impedance offered to the input signal is decided by all those parameters. Again, look for the derivation, if you feel so, in books. RB parallel beta 1 RE1 plus beta 1 beta 2 RE2 plus RE. This is the exact relation. But in any practical circuit, we will see that it is going to be close to this. Of course, you can check that up in the lab when you do the experiment in the afternoon session. Determine the input impedance experimentally and see whether it conforms to this relation or to what extent it satisfies the exact relation for the input impedance. Of course, how do you find RE1? RE2 is of course this. For RE1, which is the dynamic resistance of the base emitter junction of the first transistor, you should know the collector current flowing in the first transistor, which is not 10 milliamperes. The collector current flowing in the first transistor is your calculated IB into beta 1. Beta 1 you already know, which is 180 in our case. So beta 1 into the calculated IB is going to give you IC of the first stage. Then using this expression, substituting IC for the first stage, you can calculate RE1. RE1 will be always greater than RE2 because the operating point for the second, the IC operating point, the IC quiescent value for the second transistor is fairly larger, whereas it will be smaller for the first transistor. Both won't be operating in the same region. The operating points will be different, especially IC and IB values will be different for the two. VBE will be the same. Okay. Now, I haven't written an expression for the output impedance. The output impedance is going to be this. RE parallel RE. It's going to be too small, which again you can check. So this is used as a buffer to drive a low impedance load with a rather high impedance source, eliminating the loading problem to a large extent. That's the use of a buffer circuit, a Darlington pair circuit. Actually, as I've shown in a previous slide, Darlington pair amplifiers are available in the market for various rates of collector currents. So one such is shown there. It's a 3-terminal device. You can identify the terminals, of course, and you know which are the terminals. It's a base of the first stage, common collector of both transistors, which has to be tied to the plus VCC, and the emitter of the second stage. Now for this particular, I don't know exactly, because I have this. But of course you can get it in the sheet, in the manual. You can get it in the data sheet provided by the manufacturer. But there are differences in the manufacturing process, of course. In the amount of impurities which may come into a P-type, the amount of impurities which may come into the N-type, that make difference. Cost, voltage gain, no problem, no. You can always replace an NPN with a PNP. The only thing is that you have to change the polarity of the supply, biasing.